Well, good morning, everybody. My name is Luis Mendez. I am local co-chair of Icpeac. And I am going just to introduce our first speaker. Is Professor Thomas Gallagher from the University of Virginia, who's going to talk about Rydberg atoms and their interactions. You have something like 50 minutes, and afterwards we'll have something like 10 minutes for questions. Okay.
Thank you, Louis. It is my great pleasure to be here today. And so what I'm going to do is to tell you about some things about Rydberg atoms. It's kind of hard to decide where to start, but in any case, what I'm going to do is just tell you what they are, why they're interesting, and then go on after talking about detecting them, tell you something about the properties that people today mostly find interesting. There are many other properties, but I don't really have time to do all of them. Okay, so a Rydberg atom is actually any atom that's in a state of high principal quantum number n. So the binding energy, if it was hydrogen, is simply the Rydberg constant divided by n squared. And so if you look at the atom, if it's in a Rydberg state with a very small binding energy, it has a huge classically allowed extent. And so in fact, the radius goes up as n squared. And so these atoms are atoms in large, very weakly bound orbits. So if you have something like n equal 30, it's bound by 13 millivolts, and it has an orbital radius of about 450 angstroms. Okay, so they're just simply huge. Okay, so, and due to their really exaggerated properties, mainly their enormous dipole moments, they interact strongly with their environment. For example, if you in fact use Rydberg atoms, you can clearly see the 300 Kelvin room temperature black body radiation from this room, which actually now turns out to be important in clocks, but it's not obvious in a clock, but it's obvious with Rydberg atoms. And at the other end of the intensity spectrum, you can study multiphoton processes with Rydberg atoms. And finally, I think what makes physicists most interested in Rydberg atoms is that you can study what appear to be otherwise impossible to realize physical situations. And the public lecture this week by Hirosh will describe detecting single microwave photons in cavities. So another interesting example of this is one of the commonly used ways of detecting Rydberg atoms is actually to use field ionization. So, and if in fact I have a Coulomb potential which is distorted by the application of an electric field, you push down the potential on one side of the atom. And in fact, if the field is 1/16 n to the 4th in atomic units, the electron can just go out over the saddle point and ionize. So at n equal 20, this requires a field of 2,000 volts per centimeter. For the ground state, it requires a field of 5 billion volts per centimeter. So this is not so practical for the bound states, but it's commonly used in the Rydberg states. Okay, so today, Rydberg atoms, if you're actually producing real population, are always done by laser excitation. Okay? And so there is a very simple way of thinking about this. You can simply think of the Rydberg state excitation as the extension of photoionization below the limit. Okay? So the oscillator strength per unit energy is a constant, except below the limit, it's all concentrated into the Rydberg states. Here's n and n plus 1. So all the oscillator strength of this whole interval of 1/n cubed is concentrated in the nth state. And the resulting cross-section is simply the photoionization cross-section divided by this energy interval, with this energy interval divided by the bandwidth of the excitation, which could be the laser line width, a Doppler width, or the radiative width of this transition. But if I assume it's a gigahertz, which might be a laser line width, I in fact find that I have a cross-section of something like 5 times 10 to the minus 17 square centimeters. Okay, so it's easy. I mean, they're simply the extension of the Rydberg states below the extension of the continuum below the limit. So you can detect them in a variety of different ways. The first way people used was simply fluorescence subsequent to laser excitation. This is really simple, but it's not too sensitive because the photons go off in all possible directions. A way that I've already shown you is field ionization, which is normally realized by passing atoms between a pair of electrodes, in this case plates. It's a beam of atoms which is excited by several lasers, and applying a field pulse to the bottom plate produces ions. Actually, I guess the top plate produces ions which are detected in the detector below. I mean, of course, this has spectacularly good sensitivity. You can detect every ion, and every one of them goes to the detector, so it's 100% effective. Okay. Now, I will come back later to this, but in Durham, Matt Jones and his collaborators are detecting the Rydberg states of strontium, which have the typical configuration 5s-Nd, by exciting them to autoionizing states that promptly fall apart. I will come back to explain this a little bit more carefully later. I mean, but the kind of apparatus that you would use to do this is essentially the same as the one I showed in the previous slide. Okay, and then finally, Charles Adams in Durham has recently pioneered the notion of electromagnetically induced transparency, in which by applying the light at the transition, say from the 5p3½ state of rubidium to a Rydberg state, if you scan the laser driving the first transition, you can see these very sharp electromagnetically induced transparency resonances. And this is an extraordinarily powerful yet relatively simple to use technique. Okay, so one of the things I will often use in talking about these atoms are atomic units. So the atomic units are simply the units that apply to the ground state of hydrogen. So the unit of mass is the electron mass, the charge is the electron charge, the unit of length is the Bohr radius, the binding energy, twice the binding energy of hydrogen is the atomic unit. The other interesting number is that the atomic unit of field is the field the electron feels in the 1s state. Okay. Okay. So let's just look at a simple picture of a Rydberg states of sodium and Rydberg states of hydrogen. I mean, so in the sodium, they look more or less the same, except the sodium Rydberg electron sees sodium plus an ion, which is 10 closed shell electrons plus a plus 11 core. And if I look more carefully at sodium, in the lower angular momentum states, actually the highly elliptical orbits penetrate the core, but even if the orbits are in higher angular momentum states, which are more circular, they still polarize the core. And as a result, in hydrogen, the energies are just given by 1/2n squared. In sodium, they're all slightly lower. So if in fact you consider states of L greater than or equal to 2, the energies are only slightly below hydrogen. I mean, these are all n equals 6, but the 6p state is down here and the 6s state is way down here. These two states significantly penetrate the ion core. That is, the Rydberg orbital penetrates it a lot. Okay. So, and of course, the energies are in fact written in this fashion. In hydrogen, it's 1/2n squared, and in fact, there's simply a quantum defect that expresses the energies of sodium. The quantum defect changes very little with n, does not change with n to a first approximation, and the quantum defects for different L's are different. Okay. So actually, you can very easily just run through a whole list of properties of the Rydberg atoms, and the interesting thing about them is that they all exhibit this very simple n scaling, which I've shown right here. For example, we've already talked about the orbital radius, but then it's clear that it's maybe not surprising that the dipole matrix elements also have the same size. And this is, of course, what makes these atoms so interactive with the rest of the world. One which is perhaps less obvious is that as I raise the principal quantum number, the lifetimes become longer. I mean, so in spite of the fact that I have higher energy states, they live longer. Okay. And so why is that? And so to understand that, you simply have to write down how radiative decay occurs. Say from an upper to a lower state, the spontaneous emission rate is proportional to the square of the dipole matrix element and the cube of the frequency. Okay. So in practice, if I consider a low L state of any atom, it's the transition down to the lowest state, which is basically the frequency corresponding to the ionization potential, that is the dominant decay mechanism. So it doesn't matter which Rydberg state I'm in, the frequency is always approximately the ionization potential. On the other hand, these matrix elements change, and the matrix element to go from a high-lying state down to the ground state exhibits an n to the minus 3 scaling. Okay? And that occurs because, I mean, just consider it. Here I have the wave functions of the hydrogen 10p state, the red one, and on the same scale, here's the wave function of the hydrogen 1s state. Okay? So you can see that the only part of this 10p wave function that's going to contribute anything to the matrix element is right here. So all of the dependence on n occurs through the normalization of this outer wave function at the core, and that, in fact, is proportional to 1 over 3/2 power of n. So hence, we get that, the lifetimes at scale as n. Now, on the other hand, if you consider the matrix elements between 10p and 10d, they basically have wave functions which overlap almost everywhere, and so you wind up with electric dipole matrix elements at scale like n squared. Okay? And that's also true if I consider n equal 10, L equal 9, and n equal 8, L equal 8. They basically overlap at large radius. Okay? So what that in fact means, and they have matrix elements that scale roughly as n squared. So this decay out here from the highest L states down to the n and L just below it actually have a matrix element that scales as n squared, a frequency that scales as 1 over n cubed, and we get this n to the 5th dependence. Okay. Okay. So in spite of the fact that they have enormously, you know, they're big, they're highly excited, they live a long time. Okay. All right. Now, you would think that, I mean, actually, if you calculate the 0 Kelvin lifetimes of many of these things, they're milliseconds and stuff. Once you get up to n equal 30, in the high L states, the lifetimes are milliseconds. But assuming you're doing the experiments in a real laboratory, there's another problem which arises. Namely, the frequencies between the Rydberg states are so low that the photon occupation numbers at those frequencies are not insignificant. And in fact, they're easily somewhere above 10. So in fact, you have not just spontaneous emission, but you have stimulated emission going down, and you in fact have absorption to higher lying states. So the net result of this is that in fact, the population becomes redistributed. If you put the population in the 18s state of sodium, and you look 5 microseconds later, it's all over the place. But it's not quite all over the place. It's mostly in these p states, right? It's a dipole transition. And in fact, at 300 Kelvin, the radiative decay rate is about 20% faster than it's supposed to be. Okay? I mean, if you were to compute the 0 Kelvin rate. So in fact, what I've shown here are, in fact, the spontaneous rates falling from 18s down to the lower lying p states, and the spontaneous rates are the shaded ones, and the solid black ones are the black body rates. So you can see that the black body transitions are all to nearby states, whereas the spontaneous transitions are dominated by the transitions to the lowest lying states. Now, for 18s or any low L state, this effect is maybe 20%. If I consider the L equal 17 state of n equal 18, the little black area is the spontaneous emission rate, and you can see that the black body rate, shown in black here, is about 5 or 6 times greater. So in fact, if you have high angular momentum states, the black body decay is actually much faster than the spontaneous rate, and you never realize the 1 over n cubed that you might expect. In fact, it's pretty easy to show that since the photon occupation number actually looks something like this, you lose a factor of omega, basically, in the computation of the black body rates. And in fact, finally, when you compute the black body transition rates in total, they have an n squared scaling. So in fact, at high n, this always dominates, right? Okay. All right, so I would now actually like to return to these big matrix elements. Okay. So if you, in fact, have transitions between nearby states that are dipole-allowed transitions, they're enormous. They scale as n squared, and they actually have several interesting properties. First of all, you can drive transitions between these states with basically no power at all, practically. You can field ionize the states, which I've already mentioned. And then finally, it's very easy to shift the levels around so that you can, in fact, tune them all over the place. Okay, so let's consider, first of all, just driving an RF transition. How much power do you need to do this? Okay. So if I consider something like this microwave transition, well, this is in sodium. It's at 12 gigahertz, and so the requirement to drive this transition in a time t, which might be a microsecond, is that the product of the dipole moment times the matrix element times time has to be equal to pi in the correct units. And for a microsecond, t of a microsecond, and using this matrix element, you can immediately compute that the electric field that you need is 2 millivolts per centimeter. Okay, so some of you are probably theorists, or even if you are experimentalists. When you buy a microwave generator, it comes specified in terms of power it produces. So if I convert this to power, this is something like 10 picowatts per square centimeter. And if you buy any signal generator, it has a power of 10 milliwatts. So you sort of have 6 orders of magnitude of power to play with. Okay. So all right, I would like to then move on to considering the Stark effect. Now, I will first of all point out there's a more elegant way of doing this, which is using parabolic coordinates, which most of you probably haven't used. I had never heard of them until I came into this problem. So we're going to start out by just imagining I have n equal 2 states of hydrogen, and I'm going to apply an electric field to them. So the field is in the z direction in a couple states of the same m. And in fact, the way the levels look in an electric field for n equal 2 in hydrogen is like this. The m equal plus or minus 1 levels don't move. The m equal 0 levels split. And in fact, what happens is that the field lifts the zero field degeneracy of the s and the p state, and it produces 2 states. It produces a red state, in which the electron is on one side of the atom, and a blue state, which is on the other side. I mean, these 2 wave functions correspond to a wave function which is s plus p, and one which is s minus p. Okay, so the electron adds on one side, the wave functions add on one side of the atom and subtract on the other side. Okay, so if I simply write down the zero field Hamiltonian for m equals 0 states of n equal 2, it looks basically like this. Okay. So the point though is that you can pull the electric field out of this, and you get the same eigenstates no matter what the field is. Okay. So the states are field independent, and and they in fact have Stark shifts which are proportional to the electric field. So I guess the point that I would really like to pound on is that the resulting states here have permanent electric dipole moments. They do not have good parity. These are not like every S and P state you have ever heard of. I mean, or at least I was always told atomic states have good parity. These states don't have good parity. They have permanent electric dipole moments. Okay, so, and then this is just a picture. So the state that shifted down in energy to the red is on the side of the atom near where the saddle point pushes over, and the blue state is on the other side. Okay, so if I, in fact, go up to higher n equal 2 is fine, but if I go to higher n, what happens is that the levels of even and odd m are interleaved, and the total energy span, actually, of the m equals 0 states is 3/2 n squared e. So the state that is actually on the top of this group of states, which are often termed the Stark manifold, has a Stark shift of plus 3 n squared e over 2, and the state shifting down the fastest is minus 3/2 n squared over 2, and the spacing between the levels of the same n is just 3 ne. Okay, so if I actually look at the hydrogen atom, we have not left hydrogen in the Stark effect yet. In fact, what happens is that I can draw the levels of different n, and they actually cross to a pretty good approximation. Where they cross is often called the Inglis-Teller field, because in a plasma, that's where you lose the resolution. And they're drawn out to the points where they actually start falling apart. So the states which are shifted to the red fall apart at lower fields than the states which are shifted to the blue. But that's because in the red state, the electron is right at the saddle point, ready to leave, whereas in the blue state, it's held away from it by something analogous to a centrifugal barrier. Okay. So leaving hydrogen for atoms that people actually use for experiments. If you consider any other atom, and sodium is a reasonable example, what happens, of course, is that you have these states with non-zero quantum defects, which I mentioned earlier. So in sodium, the ones that have obviously different ones are the p and the s states. And you can see that two things. One is they sort of go out horizontally till they hit the manifold of these Stark states. But more important, there are all these avoided crossings out here. In this case, the avoided crossings are so bad that the levels are almost going out horizontally. Okay. Okay, so if I return to the question of field ionization, which I showed rather glibly before, when you do if you do an experiment and you think you're going to excite some atoms, you're going to let something happen, and then we want to analyze the results by field ionization. Invariably, you're considering a problem in which when this field pulse starts, the field is at 0, and then it goes up to the ionizing field. Okay, so that it's not completely obvious how that will happen. In fact, if you excite a hydrogen state, you, in fact, just follow these straight lines out. And if you excited, say, this state, you would just follow it out here and ionize here. Whereas if you excited this one, you would go out, ionize here. In the sodium atom, if I excite the 16s state, it follows along here adiabatically. These crossings are big enough that in realistic field ionization pulses, the slew rate is slow enough that you go through these adiabatically. And it just sort of wanders out here. Whereas 16p goes up here and does the same thing, and these ones in the middle go out, something like this. All right, so what that means then is this is sort of an abstract view of those levels. This is the region of the level crossings. So what matters is where this manifold of Stark states is. So this is the 18s state, 17d is here, 18p is here. 17d is below the Stark states, or the higher L states, and it's closer to 18p than it is to 18s. But finally, the fields at which 17d and 18s ionize are almost the same, and the field of 18p is much lower because it has all of the states that come from the high angular momentum states jammed in between. Okay, so, so the final aspect of electric fields, which is interesting and useful, is that you can tune the levels with it. Okay, so this is clear by looking at the picture of the Stark shifts. And often you're interested in tuning the fields with relatively small fields, which you can describe the shifts as a polarizability times e squared over 2. And the polarizability scale is n to the 7th. So, I mean, these numbers quickly become very, very large. However, let me point something out. When you use Rydberg states, you very quickly get out of the regime where perturbation theory works. I have listened to people explaining how they got these astronomically large Stark shifts using polarizability. But if you look at this picture, it's clear that the biggest Stark shift you can ever have is 3/2 n squared e. The biggest slope that you get is right here. And if you compute a Stark shift from a polarizability and it's bigger than that, you have left the regime where it is a polarizability. Okay, all right. So now I would like to briefly consider long and short range interactions of other atoms with Rydberg atoms. Okay. So you can divide these into sort of two classes. One is the case in which the interaction between the Rydberg atom and something else is long range, and the other is one in which it's short range. Okay, so I'd like to consider this first. Okay, so I'm going to consider, as a start, as I already made the slide, the interaction of a sodium Rydberg atom with a perturbing argon atom. Okay, and we'll start by thinking about this as a collision. So there are three binary interactions here. The sodium plus with the electron, that's just making our Rydberg atom. The argon interacting with the sodium plus, and the electron interacting with the argon. Okay. So let's start with the electron. We've already discussed the sodium plus and the electron, that's the Rydberg atom. So the one that we haven't thought about is the electron interacting with the argon. Okay. So this is often described by a Fermi pseudopotential that looks like this as a delta function interaction where when the electron basically is very close to the argon atom. Now, if you think of scattering an electron from an argon atom, the argon atom weighs about 10 to the 4th times as much as an electron. So essentially the only thing that you can do is scatter the electron elastically from the argon. Okay, so if the electron is going around an orbit like this, it runs into the argon atom, goes off in a different direction. And so when people have done collision experiments, they found that if you populated a state of high enough angular momentum that it had quantum defect roughly 0 and it was degenerate more or less with the higher L states, this population very rapidly would go out of this D state into higher angular momentum states. It's essentially just the scattering, the process that I showed you right here, namely the electron in the D orbit hits the argon and goes off in another direction. Okay, now it turns out that in cold atoms this problem has reappeared. If you actually now consider a rubidium Rydberg atom, you can also have lots of rubidium ground state atoms around, and they're not moving very fast. And in fact, the same Fermi interaction potential that's responsible for the scattering I just described can lead to bound states in the antinodes of the Rydberg wave function. Okay? And so these are in fact here the wave functions for a rubidium atom trapped in the radial antinodes of a rubidium Rydberg wave function, 30D to be precise. And this has been observed, these are often called trilobite molecules because they sort of look like trilobites. This is in fact the electron density. This is where the other, this is the rubidium plus core, and that's where the other rubidium atom is. So so the first observation of these was actually done in Tillman-Fowles' group several years ago. And these are the spectra obtained by exciting the rubidium 37, 36, and 35S states. And these things to the low frequency side, which are blown up over here, are the trilobite states. And this is the V = 0 state in that outer well. This is the V = 1, and I don't remember what the stars are. Okay, so but you can actually see these. And they, in fact, in some cases have produced homonuclear molecules that have electric dipole moments of kilo-divi. Okay. All right. Now, if I move on to consider the interaction between the argon and the sodium plus, okay, what actually happens if I bring the argon close to sodium plus is that I polarize the argon. And unlike an electron, these two don't move so rapidly. So the sodium plus basically polarizes the argon, and so I no longer just have a point charge at the origin of my atom, I have a dipole as well. And in fact, this dipole moment mixes the end states, which leads to population redistribution. So this has been observed in room temperature collisions, and actually, and also recently using cold rubidium atoms, again in Tillman-Fowles' group. Okay. Okay. So finally, I'd like to return to the other kind of interaction I mentioned, namely the long-range interactions between Rydberg atoms and something else. And while there are a couple of other examples of long-range interactions, in many ways the most interesting one are in fact long-range dipole-dipole interactions between two Rydberg atoms. Okay? And I will start by where this started, namely with collisions. Okay? So I'm going to consider the collision of one Rydberg atom with another. And in fact, what I'm going to do is use one of the notions we talked about earlier, namely the fact that I can tune the energy levels, and I can tune them with an electric field so that I can, in fact, tune the energy level of atom B so that it exactly matches that of atom A. And at that point, what I hope to see is an enormous cross-section. Okay. So a way that you can actually do this is in an atomic beam of sodium, you populate the 17s state. So you imagine that you put 2 atoms here. And in a beam, you have slow atoms and you have fast atoms, and they collide. And then you let them collide for a while, and then if you analyze the population by field ionization, you can in fact look for a population in this upper state. As you sweep the value of this tuning field, that in fact will produce 4 resonances between a pair of S atoms and a pair of P atoms. Okay. So in fact, you can see these 4 resonances. And so the obvious questions are, what's the cross-section for this process? And what's the width? So the width is actually easy to figure out because you know the Stark shifts of the levels, and so you can easily see that the widths of these things are a gigahertz. So that means the atoms are colliding for a nanosecond. It's not obvious what the cross-section is, but in fact, you know that the rate of the collisions is the number density times the cross-section times the velocity. You know the rate, you know the number density, you know the velocity, and so you can find that the cross-section is 1 billion square angstroms. Okay. So here we have 1 billion square angstroms, a collision time of a nanosecond, and typical gas kinetic cross-sections are 100 square angstroms with collision times of a picosecond. Now, okay, so, all right, so you can actually, okay, the one very nice thing about this is you don't have to be a theorist to figure out the cross-section. You can calculate this yourself. Well, okay, so we're going to imagine we have one of these atoms going past the other one with velocity v and impact parameter b. And so the initial state is 2 s atoms, and then the final state is np and n plus 1p, which are p and p prime. And this is the interaction. Okay, so for future use, because we're going to move from this to cold atoms, I in fact want to make a molecular state. The first one is the initial state, which is 2 s atoms. That's SS, which is this direct product. And then the final state is PP prime, which is this direct product. Okay? And as a function of electric field, the S state doesn't change, but the P prime state does. And it's resonant at this electric field. And they are, of course, coupled by the dipole-dipole interaction, which I've just abbreviated here. Now, the interesting thing is that at the resonance field, irrespective of the internuclear spacing, the eigenstates of this problem are always SS plus P prime and SS minus P prime, minus P. I mean, it's exactly like the problem we did in the 2s state of hydrogen. Okay, so, all right, so then what happens during the collision? Well, as I've already said, the eigenstates are always this SS plus P prime and SS minus P prime. So when you do the laser excitation at t equals minus infinity, you make the coherent superposition of these two, which is SS, which is just SS. In other words, you add this wave function to this one. Okay, so during the collision, the atoms come together, the dipole-dipole interaction spreads the two eigenstates apart, and so what I should have drawn here is when they're closest together, basically the spacing is the product of the two dipole matrix elements divided by the cube of the impact parameter. So, okay, so in fact, our amplitudes follow both of these paths, and then they're recombined here at the end of the collision. Now, if the area here is pi, then in fact I have a relative phase shift of pi between these two states, and it has now gone from SS to PP, okay? And so if you simply compute this, well, the height of this thing is mu prime over b cubed. The time is the impact parameter divided by the velocity. Set this equal to pi. You find that the cross-section is the fourth power of the principal quantum number over v. And if you work this out, that gives you, for n equal 20, and 300 Kelvin atoms, the the 1 billion square angstrom cross-section. Okay, so in fact, you can easily show that if you make these things colder, going from 300 Kelvin to 1 Kelvin, you in fact can narrow these things up to 6 megahertz. And so at some point, people began to think, well, what if you in fact had a magneto-optical trap that's something like this? So if you just blindly extrapolate this, what we've seen so far, I mean, I've shown you data that are here and here. The width should actually go down to something on the order of 10 kilohertz, and the cross-section should be something like 10 to the minus 3 square centimeters. Now we're in square centimeters, okay? So, but in fact, if you look at the characteristics of a magneto-optical trap, so typical densities are 10 to the 9th atoms per cubic centimeter, which means that the distance between the atoms sort of is 10 to the minus 3 centimeters. And the velocities in the trap are something like 20 centimeters per second. Okay. So what this means, okay, so let's compare this to n equal 30. So if I have an n equal 30 atom, the radius or the diameter is 10 to the minus 5 centimeters. So that's 1% of the spacing. It's insignificant compared to the size of one of these dots. So, and in 1 microsecond, the motion is similar in size. So for all practical purposes, if an experiment happens in 1 microsecond, these atoms are essentially frozen in place and are more like a spin glass than anything else. In other words, it's no longer a collision problem. It now has become basically a form of, well, it's not really, but it's like almost like condensed matter physics. Okay, so experiments along this line were done in several laboratories, and what I will show you are data obtained at Laboratoire Aimé Coton in the group of PRPA. So they in fact excited 2 cesium atoms to the 23p 3/2 state right here, and they in fact looked for transitions, resonances that would take a pair of p atoms up to the ns state, which is it's 23s down here and 24s above it. Okay, and in fact they observe exactly the same thing. Well, they observe resonances that, as they raise the density, become broader, which does not happen in the collision experiments. So you can actually understand these in the same way that as you understand the collisions, but you have to change your picture a little bit. In the collisions, as a function of time, the radial position moves, and so we're moving along here. If you consider when atoms are frozen in place, basically what happens is they're frozen either here or here or here. And so this isn't really a very good way of drawing it. A better way of drawing it is like this. Okay? So depending upon how far apart the atoms are, and of course it's a random gas, you don't really have too much control over how far apart they are. So you still have the same pair of eigenstates, pp plus ss and pp minus ss prime. And what you do, in fact, with a pulse laser, once again, is that you excite the coherent superposition of these. The laser pulse is short compared to this line width. And so you make this coherent superposition of both of these. They have an energy difference, and so it's simply a quantum beat experiment. In fact, what happens is that they oscillate back and forth between pp prime and ss prime, okay, at this frequency. But since I have atoms with varying frequencies, I not only have this frequency, I have this frequency. So it's kind of a blur, but you still can see the population transfer. But you can't see you cannot see the oscillation back and forth. Okay. All right, so if I move on from this, so there are several other interesting applications of this kind of notion. One which has been proposed by Lucan as a means of making a quantum gate is called the dipole blockade. And the idea is quite simple, that if I in fact excite one Rydberg atom here, say this is using rubidium, I can excite the first one, it's fine. But when I try to excite the second one, if in fact there's a dipole-dipole interaction between these two, I can't because the levels are split. Well, just to make this a little, so they're split basically in this fashion. And as long as the size of the atom, or sorry, the size of the cloud D is such that I can resolve these two states. I cannot excite the second atom. Okay. Now, Lukin actually proposed doing this with permanent moments in a static field. That means, say, using a state like this. However, this turns out not to be practical because the field inhomogeneities reduce the resolution and you simply can't separate those two states. So a better way of doing this is using the van der Waals interaction, which is simply the off-resonant case of the dipole-dipole interaction we considered just a few minutes ago. So for example, here is SS and here's PP prime. They are separated by an energy delta, and the van der Waals shift of this SS prime state, which you can reach with the laser, looks like this. It's just the dipole-dipole interaction squared divided by this detuning. And this, okay, roughly scales as n to the 11th. Okay. However, I would like to point out one obvious thing. This actually, again, has the same problem of the polarizabilities. This is a perturbation theory expansion. First of all, it's not true that delta is a constant divided by n cubed, which is an assumption that went into this exponent. Often delta can change sign. And the other thing that's true is that once, in fact, the atoms are closer together than what I would call the van der Waals radius, where the dipole-dipole interaction itself is comparable to the detuning, then in this regime, it's simply a 1 over r cubed dipole-dipole interaction. Okay. Okay, so the other wrinkle of this is something called Rydberg dressing, introduced by Peter Zoller. And the idea is very, very simple. The motivation is that is to give ground state atoms, which are there forever, these exaggerated properties of the Rydberg states. Okay. So the idea is a slightly off-resonant laser couples the ground state to the Rydberg state, making a new ground state, which is mostly ground state with a little bit of Rydberg state. Okay. So the point is then that the van der Waals interactions between these two ground state atoms is actually given by this omega is the Rabi frequency, and delta is the detuning, times the van der Waals shift of the Rydberg state, which in fact can exhibit this n to the 11th scaling, but with the caveat I already mentioned. Okay, so in the remaining few minutes that I have, I would like to move on to the Rydberg states of two electron, well, what I call two electron atoms, really two valence electron atoms. And what's interesting about them, as opposed to, say, rubidium, is that you can easily excite with a laser the electron of the other valence electron, that is the electron of the core. And I've already mentioned the fact that you can detect these atoms by autoionization, but there's more. Okay, so to understand this, let's just look at an example, barium, which is two electrons outside a closed shell core. So let's take one of those electrons away, and I'm left with barium plus, okay, which is isoelectronic to cesium and has an energy level structure that's very similar. The 5D state in cesium is higher. But the transition from 6s to 6p in barium plus also has an oscillator strength of 1. Okay, so to each of these levels of barium plus, you can now add the other electron. And so you get Rydberg series and continua above it. Okay, so these are the bound Rydberg states right here. But they're completely analogous series converging to other states of the ion. Okay. All right, so there's only one page that looks like this. So you can actually write down the Hamiltonian for this. And I've written it in the following way. We're ignoring the spin. So these are the kinetic energy operators for the two electrons. And F is the potential, or F of R1 is potential R1c due to the barium plus. It looks as 2 over R as R goes to infinity. And 1 over R12 is the interaction between the two electrons. If I write the Hamiltonian in this way, I in fact have something which is separable, and I can write the total wave function as a wave function which is a product of the barium plus wave function for R1 and the hydrogen wave function for R2. Okay, and so the energies are obtained by just adding those two energies. And in the approximation that I basically have ignored the higher order multiple terms due to the interaction of the two electrons, decay occurs by radiative decay. I mean, I could, in fact, start in a 7s NL Rydberg state, fall down to a 6p NL Rydberg state, or I could start in a 6d NL Rydberg state and fall down to a 6d some other state, but still with a 6d ion. Okay. On the other hand, when I introduce the higher multiple terms, that is H1, I introduce several phenomena, and from our point of view today, the most interesting one is autoionization. That is, this 6p NL state can autoionize into the continua above the 6s state of the ion or the 5d state of the ion. And the autoionization actually happens quite rapidly. And but autoionization isn't the same for all the states, and in fact, it's interesting to consider a nice classical picture of this. Okay. So here I, in fact, have my outer electron in an orbit. And you can think of autoionization as the electrons, the Rydberg electron scattering from the barium plus ion, which is excited. If it undergoes a superelastic collision, it de-excites the barium ion, and it leaves with the energy. Okay, so that simple-minded picture of this tells you right away that the autoionization rate is proportional to 1 over n cubed, because 1 over n cubed is the Kepler frequency. Okay. Now, okay, how likely the electron is to scatter depends entirely on the shape of the orbit. If it's a highly elliptical orbit, the Rydberg electron comes near the core, and if it's a nearly circular orbit, it never comes near the core. So you expect, in fact, to have a 1 over n cubed scaling for the autoionization rate, and autoionization rates that fall very rapidly as a function of L. Okay, so now it turns out that, okay, the easiest way to study autoionizing states is also the most interesting if you're interested in playing around with bound Rydberg states. So in fact, if I wanted to study the 6p NL states, the autoionizing states, the easiest way to do it is with a laser, make a bound Rydberg state, in this case a 6s15d, and then I shine light on it at the transition frequency for the barium plus to go from 6s to 6p. Okay? So, I mean, and in fact, the simplest way to think about this is this excitation method, which is often called isolated core excitation, is that I'm exciting the barium plus ion, it's the resonance line of the ion, and the outer electron is just a spectator. Okay, so if I, in fact, populate the 15D state with these first couple of lasers and scan the wavelength of this laser, I, in fact, see a nice peak. And right at so this is the total energy here, but it's roughly at the frequency of the ion. And, in fact, the width of this peak gives me immediately the autoionization rate of the 6p state, 6p 15D state in this case. So I guess since in the back you probably can't quite read this, but it's about 20 wave numbers wide. Okay? That's 20 wave numbers wide, whereas the radiative width of this state, that is the likelihood of it decaying by radiation, is much lower. The radiative width is 35 megahertz. So for the 6p ND state, the radiative width is completely insignificant, and decay is entirely by autoionization. Okay. Now, okay, I can't resist showing. Actually, if you raise the laser power, you see spectra like this, that you can actually explain by just extending that simple picture I gave you of projecting the outer electron as a spectator. Okay, but okay, from our present point of view, the most interesting thing is that if I raise the L of the outer electron, the autoionization rates fall really quickly. So this is the D state, which I just showed you. This is barium. They fall almost a factor of 5 with each increase of L. And by the time I'm out to L equals 8, the autoionization rate has actually fallen to the radiative decay rate. So at this point, these states do not decay by autoionization. They decay by radiation. Okay. So, okay, so to summarize, if you do this isolated core excitation of a low L Rydberg state, you always get autoionization. Well, I shouldn't say, if you raise n enough, you won't, but you have to raise it really high. On the other end, if you excite the high-lying states, the decay occurs by fluorescence. This electron stays out here in the high orbit, and the ion just gives off its photon. Okay. So the difference between these states has been used by Tom Killian to, in fact, make bound Rydberg states of strontium and observe that they, oops, I didn't write this. Observe that they, in fact, go to the higher L states and to ions. Okay. So the idea of this is pretty straightforward. If you make 5s49s, you try to excite it to 5p49s with light that's 3 times the resonance line saturation intensity. This cross-section is so broad that the cross-section is suppressed so much that nothing happens. The cross-section at any wavelength is just too small. On the other hand, if these atoms collide with each other and wander out to higher angular momentum states, the same oscillator strength is now compressed into something 35 megahertz wide. And when you excite it with the laser, you get copious quantities of fluorescence. And similarly, if they've actually become ions, which are now indistinguishable from high L atoms, you get lots of fluorescence. And this is simply showing at t equals 0, you get no fluorescence. And if you wait 10 microseconds, you get a lot of it. Okay. So in my final -2 seconds, I'll just mention one last thing. So the notion of having these high L Rydberg states suggests that maybe you can actually trap them. I mean, after all, if I have a strontium Rydberg state, strontium plus looks just like rubidium, and there's no reason why I can't trap that the same way that you trap rubidium in a MOT. I mean, the basic idea is if it's in a high angular momentum state, this electron, if it starts in 5s and L, just stays here. You excite the ion up and down, it fluoresces, and it will just stay there happily for a long time. So this hasn't been done yet, but several people are trying. Okay, so the notion I would like to leave you with is that the exaggerated properties of these Rydberg atoms make them really easy to manipulate, and they present many unexpected opportunities. And thank you for your attention.